Okay, hi. Another test, another example, running a test and then computing probability of type 2 error for the test. So we have this little table here, two populations. One is 37 students, let's say, that play school sports, and there's a dexterity rating, which is YI for each of the 37 students. The sample mean is 32.19, and the sample standard deviation's 4.34. The ones that don't play school sports, you see it there. Slightly lower sample mean, slightly higher sample standard deviation, and same number of students in that population. So we're asked to use a alpha equals 0.05 level test to determine if the students who play sports have a higher degree of dexterity, and as well to calculate the probability of a type 2 error in the case that the difference in dexterity rating is 3. So yes, you would not want to make an error. In that case, it should be pretty low. But let's see. Okay, so let's see. So first one. So what's the test statistic for the first one? So first, let's write down the null hypothesis. I'm going to write it down using the equality now. Let's emphasize the new. So we'll have mu1 minus mu0 minus mu2 equals 0. This will be my null hypothesis, and to argue that population 1 mu is higher, HA will just be mu1 minus mu2 is greater than 0. Test stat is, as before, when we were looking at differences of means from two populations, will just be the difference in the sample means, and the rejection region will be upper tail, right? So y1 bar minus y2 bar greater than k. Okay, so we see k, so that alpha is 0.05, right? So I think the next thing is to get k. Can't hurt, you can always write this to help organize you. To find k, we need, okay, we're considering alpha equals 0.05. So we want probability of type 1 error, alpha, equals probability of a type 1 error. So that's the probability that we reject y1 bar minus y2 bar is greater than k, given mu1 minus mu2 is equal to 0. If I use the composite hypothesis here and made this less than or equal to 0, I would still be using equals 0 here, which is at the boundary and bounds alpha. So it's just not any different. Okay, so at this point, yeah, you're ready to use the central limit theorem. That's why we call these, this is why these are called large sample tests after all. So, yeah, here we are. Okay. So, what are we doing here? So, okay. So, alpha, probability I reject, given H0. And, right. So, what is the distribution of y1 minus y2? y1 bar minus y2. So we have y1 minus y2 bar is approximately, right, normal. So this is approximately normal, mu1, mu2, mu1 minus mu2 is the mean, and then the standard deviation is S1 squared right? So S1 squared over N1 plus S2 squared over N2. Actually, I know why I'm confused. This should be sigma 1 squared and sigma 2 squared. Okay, there we go. Sorry about that. All right, so here we go. So now we're going to, again, approximate these. Also, N1 equals N2. So I'm going to approximate these with, so also approximately, normal mu1 minus mu2. And we'll write S1 squared plus S2 squared over, this is the same one here, so over N. Okay. All right, so alpha then is equal to probability y1 minus y2 is greater than k, given that, so let's write it, probability y1 bar minus y2 bar greater than k, given y1 bar minus y2 bar is normal, mu1 minus mu2 is 0, so 0. And here I have S1 squared, so I'll just write it like S1 squared plus S2 squared over 37. Okay, and this is equal to, so, and I should say approximately, right, from the central limit theorem. Okay, so this, though, is equal to probability z is greater than, okay, I subtract off 0 from, so I don't subtract anything off here, right? It's just 0, so it's k minus 0. And now I divide by the square root of this, right? So, so times, if you want, times the square root of 37 over S1 squared plus S2 squared, which I have to get from the table, right? We still have that from the table. If I do all this, what do I get? I get, well, I didn't do it yet. So if we want, so for alpha equals 0.05, this means that k times 37 over S1 squared plus S2 squared should equal Q norm 0.95, which is equal to 1.645. So K equals 1.645 divided by the square root of 37 times the rest of the stuff, square root. I actually never did this piece out separately here, I don't think. And I get this is equal to 1.702. Okay, so I want to reject and claim there is significant difference if the difference in the two sample means is 1.702. So this gives me my alpha equals 0.05 test. So let's write that. So our alpha so since is actually equal to, let's see, 32.51, we do not find evidence that population one has higher dexterity. Okay. Oh yeah. So we have to do the second part. So to calculate the probability now of the type 2 error, this part, we want to find the probability of type 2 error. So to find, okay, so B beta mu1 minus mu2 equals 3. Let's just say is equal to the probability that, so this is the probability we don't reject when the difference is 3. So this is the probability that y1 minus y2 is less than 1.702 given mu1 minus mu2 equals 3. Okay, so if it's less, right, we don't reject, less than or equal, and so that's the definition of a type 2 error. So it's the probability we choose H0 given a certain value of the parameter in the alternative hypothesis set. So we're here, we just need to go through a similar process again. So this is equal to probability. Now, this time, and again, this is approximate, right? Approximate CLT. Probability that, well, not that different. Y1 minus Y2 is less than 1.702 given y1 minus y2 bar is normal, mean 3, and same, we did not change the variance, right? So mean 3 and the variance would be, well, let's write it this way, sigma 1 squared plus sigma 2 squared over 37. We'll approximate that again with the sample mean, so sample deviation. So this is approximately the probability z less than 1.702 minus 3 divided by this whole thing, square root s1 squared plus s2 squared and square root 37 up here. All right, if we do all this, I get, this is equal to the probability z is less than, if you want, equal to minus 1.254, just computing this. And this is about 0.10. Okay, so this is your answer. It's about a 10% chance of a type 2 error, even when the difference in the means is as much as 3. Okay, so it's a little high. Now, that's that example. We want to talk about sample size next because that's sort of the answer. We fixed alpha here and we solved for beta. One case it was pretty high, it was a half. The other case we made the value of the parameter in the alternate hypothesis significant in there, 3, pretty far from 0, and it was still 10% still. So the way to deal with this and make the type 2 error go down is to take a bigger sample. We'll look at calculating sample size to do that in the next lecture. Stay tuned. Click on the next lecture at your convenience or now.